So this is my motto, and you can read, it's Einstein's motto in principle. Let's read it, that nature is, subtle's nature, but devious nature is not, yeah. So how I got interested in the subject, of course, if you are learning quantum mechanics, it's very strange that theory giving statistical predictions is claimed to be the most complete description of the individual system. So this is difficult to accept, and liking writings of Bohr and liking writings of Einstein, I was thinking about the problem, and of course, in some time of moment, you are coming to hidden variables, you read about Bell theorem and things like this. And I think I found, and some colleagues we found, that contextuality, in some sense, is reconciling Einstein with Bohr. So let's see, I'll try to convince you about it. So what is my philosophical standpoint? The moon does continue to exist even I do not look at it. Probability is objective. This is important point. Probability is objective contextual. It's moving, yeah, so it's... the probability is an objective contextual property of some random experiments and not a subjective belief of some intelligent agents like in QBIS. And there is no need to reject causality and locality in order to explain EPR paradoxes. Since I wrote many papers starting from when I met Bell in '76, I thought that my paper in physics letter in '87 solved everything, but apparently not. So we are still struggling to pass the message through. So many full text of my old papers are here, so of course you can find them. So in my opinion, the paradoxes are created by people describing in correct ways the theoretical models and experimentalists by interpreting incorrectly the experiments. So here I give some citations by famous physicists, which simply are just misleading. So for example, this is each die is random and fair. Its entangled partner somehow gives a correct magic outcome. It's completely impossible. An electron is indeed both here and emitter to the right of here. Impossible. Schrödinger paradox and so on. So quantum non-locality. Quantum non-locality appear to influence particles, appear to influence one another instantaneously. It is well-established experimental fact, mystery. Correlations are coming out of space. So continuity principle violated. Explanation by causes belonging to the common past. Explanation for the correlation by a first event causing the next. This explanation failed. Nature is non-local. I want to convince you that explanation one did not fail. So now we propose, some famous scientists propose a new law of nature. We must accept non-local randomness and irreducible randomness that manifests itself in severally widely separated places without propagating from one point of space to next, producing at the same time strongly correlated outcomes. I have a question. We have a nice bird, which is, I like birds. I like 2 years ago, I was talking about butterflies. So we have the small bird, which is doing migration from Alaska to New Zealand. And he's flying 18,000 kilometers in about 8 days without stopping to rest or refuel. How could they do, these birds, do it if non-local randomness was a law of nature? So plan of this talk is EPR paradox statistical interpretation. I'm sorry, this is very naive and not very popular now. This will be contextual statistical interpretation, but this is interpretation which I like and I find practical. You have SPCE, it's spin polarization correlation experiments, long-range correlations, counterfactual definiteness, finite sample proofs of different inequalities, impossible quantum random challenges of Wonger and Gill, contextuality and local causality versus non-locality. And if I have a time, I would like to talk to you about some recent result about sample homogeneity loophole, which make statistical conclusions from the experiments invalid. Okay, so quantum orthodoxy, 1935, individual physical system at t equal t, you have unique wave function, and we have this collapse that measurement is reducing this wave function to another wave function. Yeah. So EPR paper found that if you have a system in EPR state, single measurement performed on one of the systems gives instantaneous knowledge of the wave function of the second system moving freely far away. And it means it is possible to assign two different wave functions to the same physical reality, the second system after the interaction with the first. So this, it should be unique to individual system, it should be unique wave function associated. So shredding told no matter how far apart the particles are, when we try to collect one, they are not really free. We have entanglement, quantum steering, mystery, spooky action in the distance, etc. So Einstein gave in 36 answer, explains that there's no paradox. Is psi function does not in any sense describe a state of one single physical system. Reduced wave function describe different sub-ensembles of the systems. Valentine perhaps went a bit further, but and he thought of considering an individual particle to have its own wave function is strictly incorrect. So what is statistical interpretation? We have identical state preparations, which are repeated. We have wave function of density metrics, and we try to do predictions using quantum formalism. So in EPR bomb version of paradox, we have singlet state, and we know that when we make measurement on one direction, on one particle, the second particle, we have a reduction of wave function. So in EPRB, there is no paradox in statistical interpretation because the reduced state plus P describes the ensemble of partners of the particles which were analyzed to have spin down by analyzer P. It's like an ensemble related to some post-selection, which was present in many talks here. For various directions P, there's different ensemble. Even if the anti-correlations were strict, there is no paradox. I was talking about more in detail in 2006 in the conference in Paris. And what we have now with this paradox, we have this famous non-local correlations paradox. We have two correlated signals propagating in opposite direction. We have clicks on distant detectors. And Bell and followers saying all local models predict this inequality. So what I will try to show that not all local models. So this is ideal scheme, which already initially was proposed by Bell. To generalize the case, we have two correlated signals, S1, SS2, produced by the source and hitting measuring devices, XY, and producing correlated outcomes A plus minus, B plus minus. So what is correlation? It's very clear to say correlation if you have somebody, you have some population, you have balls which are red, which are from metal, and you can find all properties of the ball, and you have joint probability distribution, and of course you can find correlations of the different attributes. If you have data in distant laboratories, it's impossible. It's completely different kind of correlations, and generalized JGPD is a generalized joint probability distributions. So simply, let us imagine two experiments. We have two samples, A1, AN, B1, BN, and the problem is how to find this generalized joint probability distribution. It's not unique. It depends how you pair these distance outcomes. It's not unique. So it depends on protocol of the pairing. Let's see as a very simple example. Imagine that you can have a pairing. You take first observation with, you start with the first observation in a sample A, Alice, and BK of Bob. Yeah. So this is pairing S1K. You have random pairing SR. You pick up just outcomes from one experiment, another experiment. They are chosen at random. So in this simple example, if you took S1K pairing, K odd, you have strong anti-correlation. If K is even, you have strong correlation. If you take a random pairing, you have no correlation. So once pairing is defined, in this moment, you can define generalized joint probability distribution, and correlations may be estimated. In general, they don't factorize. So the correlations do not prove any causal relation between X and Y. No communication or direct influence between X and Y is needed for their existence. So I mentioned in the idealized model, you talk about strict anti-correlations. And it said it's prediction of quantum theory. It is simply not true. Quantum theory, in understanding of how you apply it, are giving formula, but we don't have in nature sharp angles. So this has to be treated in some sense like a density probability. You have smeared it out to get predictions. So quantum theory gives you predictions. You have small intervals around the directions. And already in '87, I mentioned it, and that there is no strict anti-correlations predicted by quantum theory. Now, what happens in spin polarization correlation experiments? So the situation is much more complicated. We don't deal with the singlet state. We have Werner state, Eberhard state, Keffler et al. State, very complicated mixed states. So surely we have no anti-correlations in real experiments. So coming here, how people were trying to explain correlations and derive Bell or CHSA inequalities. So I wrote several papers giving some probabilistic arguments about protocols of experiment, but probably it was too complicated, so I tried to analyze very simple proof given by Gill and very influential paper. It was Gill paper 202-203. And in this paper, imagine very simple thing. You have a source, some computer, you have 5 computers sending the 0-1 correlated time series, or samples, yeah. Measuring devices produce changes in 1 minus 1, and you have randomizer, which puts a label of the measurement, which you can make for Alice or Bob. So messages should contain as 50% of zeros and ones. Because we have these randomizers, as you remember, we have random pairing. So if they were correlations, they are destroyed. They are only such correlations in a stochastic hidden variable model. So it doesn't matter what source is doing, because randomizers are simply destroying it. So Gill result, however, his finite samples may violate, say, these equations, but probability of large violation is small. Similar reasoning was done by Gill and al. In PNAS publication, by Wonger, etc. So what is this? This is based on this type of reasoning is similar to stochastic hidden variables. But you can also go to the like a first Bell proof when he was using that everything is determined. You have joint probability distribution. So this was using so-called counterfactual definiteness, CFD. So a physical system is characterized by some well-defined attributive properties. Imagining apparatus is reading with possible mistakes and with the predetermined values. But in SPC, the outcomes of all measures on the photon pair and in SPC are predetermined by the source. This, as even Chaslav, which I thought that he has the same interpretation now about non-locality, wrote in his paper that counterfactual determinants contradicts Qt, but recently told that he, however, disagrees with us. Okay. So counterfactual definitely is proved by CSS bar Gill 214. Gill papers are cited in this Nature paper about new experimental result by the Dutch group, 3 Gill papers. So how he's trying to make a proof? So the outcomes are predetermined attributes of incoming photon phase. AA prime, the spin projection for Alice particle, and B prime. So you have 4n subsequent pairs are described by 4n by 4 spreadsheet of numbers plus minus 1. The rows are labeled by index j up to 4n, columns by 4 attributes. So I will, of course, not give proof. In my paper to proceedings, I will give more details. So this is like a table for 4 pairs. Yeah, this is properties, predetermined properties of the particles, you know, for pair 1, pair 2, 3, and 4. So what Gill is doing, he is deducing from this sheet a sample for setting xy prime. Please note that this column, if you have this spreadsheet, and if you change B prime to B, of course, this column cannot change because it was predetermined. So if he does it, we get another. This column is the same as it was, and here is B, which is different, of course. So the outcomes are not predetermined, and 4 and 4 spreadsheet cannot be constructed for spin correlation experiments. And this, if you look at this spreadsheet, it defines a random samples drawn from joint probability distribution, normal, not generalized, for 4 random variables like local, realistic, hidden variable model. So SPC are experiments for which generalized joint probability distribution do not exist. Bulv, Vorobiev, Andrei, Hansi, Tamar, and so on. I will still give names later. So what happens in spin polarization correlation experiments? You have simply, you don't have these outcomes. You have for first pair, you have this. Of course, you have non-registration. This is, so you see it's completely different. And you don't get samples like Gill obtained. We obtain something like this. So quantum Randy challenges. Now it's very popular. Wonger wrote a nice paper about it, Gill, and you can read about it and what it's about. So Wonger, for example, goes with the same model of photon pair, and I should perhaps mention that I have no idea what photon is, how I should imagine it. Yeah, it's a useful notion, but you can say it's one particle state of the quantized field and things like this, but of course, I don't make any pictures. So deterministic instruction on each ball tell whether output is 0 or 1 according to the angle it encounters. So for each pair of balls, we may fill 1 row of 800 for counterfactual spreadsheet discussed by Gill, but now instead of -1, we input 0. He put some conditional strict anti-correlations. No, I don't believe it. It's impossible. So you should tell me now. It's I was not okay. So if it's okay. So this is so QRC is saying simply this. So that you have to generate such a spreadsheet and after violate more than 50% this inequality. Okay, so I will go simply, I have to skip something. So finite sample proofs are based on this local Bertelmann-Stokes model, pairs of dice model. What is nature's local strategy? The outcomes are neither predetermined by a source, by choice of settings, the outcome not randomly. The outcomes plus minus 0 are produced in deterministic way. So we have something else. We have here with each outcome is related lambda 1, characterizing signal, lambda x, which characterize measuring device, and so on. So this is contextual causal diagram. You see it differs from the diagrams which you saw at the beginning of the conference. We have here lines like this with here we have free choice to choose our settings. With each setting, we have some subspace of supplementary parameters, which is here, which signals which are here describing, and this lead to the results. And simply, yes, and we have contextuality. Each random experiment has its own probability space. And we have local probabilistic model, which can describe, you see now it's lambda x, y. You don't have, and you have existence of common probability space was taken for granted. It's not, and you have fatal contextual loophole of Theo, and people don't mind it. And it was noted by very many people. I have to go quickly to free will. Just I take free will and I stop. So choice of the setting X does not depend on supplementary parameters. This is very important. I believe in this. Of course, if you are super determinist, it would depend. It doesn't depend. I believe that we have free will. But of course, lambda A depends strongly on X, because in lambda A, we have lambda X. Reasoning based on symmetry is false, so simply I put here my diagram. Conclusions. Violation of Bell-CH, because these inequalities are implied by stochastic hidden variable model, because you have, and they are violated, you have no irreducible randomness. Emergent quantum theory, description of subphenomena. So you can read more in my papers, which I recommended you, and also in the paper in the proceedings. Thank you very much.